Hi, in this presentation, I'm going to talk a little bit about Dijkstra's algorithm. So Dijkstra's algorithm is used to find the shortest path between any two vertices. So we can see a vertex is from like one point to another or any point. In routing networking, we think of these as routers or layer 3 switches. So we will find the shortest path from, in this case, vertex A, which would be our starting vertex, to all other vertices. In networking, each router would do this independently, thinking of itself as the starting vertex. Okay, so ultimately what we want to do is, starting at A, in this case, our starting vertex, we want to find the shortest path to each vertex. And we can see the path there in red. And those numbers on each of those connections between the vertices, those are costs or numbers, and what we're looking for is the shortest path. So let's look at what the shortest path to each vertex actually is and how to build this table. Later in this presentation, we'll see how Dijkstra's algorithm is used to do this. Okay, so to understand this table, we have a list of vertices, the shortest distance from A, and a previous vertex. So let's start with the starting vertex itself, vertex A. Okay, the total shortest distance from A to itself is 0. And that's what we show in the table. The previous vertex before reaching A would be, well, there's nobody else, just A. So we don't need to put that in the table. Okay, the next vertex we'll look at is vertex B, a neighbor of A. Vertex B, the shortest distance from A to B, as we can see, is 1. And the previous vertex before reaching B is A. Vertex C. Vertex C, the shortest distance from A to C is 3. And the previous vertex before reaching C would be B. And notice that all this information is being added to our table as we go through the list. Vertex D, the total shortest distance from A to D is 2. The previous vertex before reaching D is B. So counting up, A to B is 1, B to D is another 1, that's 1 plus 1 is 2, and the previous vertex is B. Okay, vertex E. The shortest distance from A to E is 5. The previous vertex before reaching E is, obviously, as we can see in the diagram, C. Last but not least, vertex F. The shortest distance from A to F is 4. The previous vertex before reaching F is D. Okay, so we can trace the path using this table. The previous vertex gives us actually the shortest path, and we can do this little trace here. So to get from A to F, okay, before we reach F, the previous vertex is D, which is shown in the table. To get from A to D, that's done via B, which is for D, B is the previous vertex in the table. And to get from A to B, well, is via A, our starting point. Okay. So the previous vertex gives us the shortest path to a vertex from every other vertex. Take a look. If we start here at A, and we can see that A is the previous vertex to reach B. And then we can see B is the previous vertex to reach D. And D is the previous vertex to reach F. Okay, let's see how Dijkstra's algorithm is used to generate this information. Okay, so here's Dijkstra's algorithm. And this isn't going to make sense to you right now, but it will in the upcoming slides, because this is the algorithm we're going to be using to generate that table. So start with the distance from the start vertex to itself, which is 0. The distance to all other vertices from the start vertex is currently unknown, or infinity. Then we're going to do a little repeat loop. Select the unvisited vertex with the shortest known current distance from the start vertex. For the current vertex, examine its unvisited neighbors. For the current vertex, calculate the distance for each neighbor from the start vertex. If the calculated distance of the vertex is less than the known current distance, update the shortest distance in the table, update the previous vertex, then add the current vertex to the list of visited vertices, and do this for until all vertices have been visited. And you're probably going, what? Unless you've seen Dijkstra's before. And then still you might be going, what? Okay, let's take a look. All right, we have two lists here. Okay, we have on the left there the unvisited vertices, which is everybody at the beginning, and then the visited, which includes nobody. Okay, our starting vertex is A. So this is, you know, if you're thinking in terms of networking and routing, this is the router itself that is running Dijkstra's algorithm to find the shortest path to all other routers. The distance from A to itself is 0, and that's shown in our table. The distance to all other vertices is currently unknown, so we'll just put infinity. Okay, so we're going to start with the unvisited vertex with the smallest known distance from our starting vertex. Well, that's A itself. For the current vertex, we look at its unvisited neighbors. Okay, so our current vertex is A, and its unvisited neighbors in the unvisited list there are B and C. Okay, so the algorithm says examine the distance of each neighbor. So we're going to examine the distance of B and C from the start vertex. A to B is 1, and A to C is 5. Our algorithm states if the distance to the vertex is less than the known current distance, which is in our table, then update the shortest distance in that table. Okay? So we can see our distance, our calculated distance is now from A to B is 1, A to C is 5. In our table, it shows as infinity. So because our current distance is infinity, both entries will be updated with these new calculated distances of 1 and 5. And then this will become more evident as we go through this. We'll see how this works. Okay, next we update the previous vertex for each updated vertex. So in our table, B's previous vertex is A, and C's previous vertex is also A. At least that's how it stands right now. In other words, both B and C were accessed via A. Next, we add A to the list of visited vertices. So we move it from the unvisited list to the visited list. Okay, now our algorithm is going to repeat. And this is where we begin to see how all this really comes together. All right, so we select the unvisited vertex with the smallest known distance from the start vertex. So looking at our unvisited list, B has the shortest distance of any of the vertices in our unvisited list. Okay. Has the shortest distance from A, which is 1. So we're going to start there. Okay. So B becomes our new current vertex. For B, examine the distance to its unvisited neighbors. So it has, in the unvisited list, it has 2 unvisited neighbors, C and D. Now remember, A is now in the visited list. Calculate the distance of each unvisited neighbor's vertex, C and D, from the start vertex of A. Yep, that's correct. All right, so let's take a look. So we're going to look at vertex C first. Remember, we have 2 of them, C and D. Let's take a look at C first. So the distance from the start vertex from A to B, which we can see in the table, is 1. We're going to add the distance from our current vertex B to C. That's our unvisited neighbor, right? We do that addition and we get 3. That's the total distance from the start vertex A, because we already know that distance from A to B, and we've just calculated from B to C. We've added that to it, and from A to C we get 3 total. Okay, now the algorithm states, if the distance to the vertex, okay, C, is less than the known current distance, then update the shortest distance in the table. Okay, let's go to the next slide and look at that again. Again, if the distance to the vertex is less than the known current distance, then update the shortest distance in the table. The shortest known distance from A to C is 5. That's what our table is currently showing. Okay? However, we have just calculated a new shortest distance from A to C, which is 3. So we're going to update the current value 5 with the new value 3, and we'll update the previous vertex A with the previous vertex B. So we just made a new entry. We found a new shorter path. So notice now our shorter path from A to C is no longer that lower link there of 5, but it's through B with a lower cost, a shorter path of 3. Okay, we have another unvisited neighbor we need to look at, and that is Vertex D. Okay, so again, the distance from our start vertex A to B, you can see that in the table, is 1. We're going to add the distance from B to D, which is 1. Add that together, and we get a total distance from the start vertex A to D of 2. Okay, and again, if this distance to that vertex D is less than the known current distance, whatever's in our table, then update the shortest distance in the table. Okay. So the shortest known distance from A to D in our table is infinity. Okay, as shown in the table. Oops, I've kind of cheated there. I've got the previous vertex already shown. Okay, we have just calculated a new shortest distance from A to, that should say D. Oh, I'm sorry, D of 2. I'll make a correction in my slides. Okay, so we're going to update the current value infinity, which is 2, and update the previous vertex, which was already done in my little animation there, to B. Okay, so we have a new shorter path to D. All right, so now we're going to add B to the list of visited vertices. So we're going to move B from the unvisited list to the visited list. Okay, once again, our algorithm repeats itself. So this is that repeating loop. Select the unvisited vertex with the smallest known distance from the start vertex. Well, looking at our unvisited list, okay, and looking for the shortest distance from A, well, that would be D. So that's our new current vertex. For D, examine the distance to its unvisited neighbors, C and D. And again, the key there is unvisited neighbors. So B is in the visited list. Okay, so as the algorithm states, calculate the distance of each unvisited neighbor vertex, which is C and F, from the start vertex A. So let's start with C. So the distance from our starting vertex to D is 2. And actually you can see that in the table. Add 2, the distance from vertex D to C. And we get a total of 4. That's the total distance from the start vertex A to C, but via D. Okay, and the algorithm states if this distance to the vertex, in this case C, to vertex C, is less than the known or current distance in our table, then update the shortest distance in the table. All right, so let's take a look. The new calculated distance is 4 to vertex C. Okay. Well, we already have an entry to C, a shorter path, which has a distance of only 3. So the table is not updated in this case. Okay. Remember, the shorter path is to get to C, and we can see that in our table, its previous vertex is B. So that's the shorter path. And since this is a longer path, we're not going to update the table. Okay, we had another unvisited neighbor, and that is vertex F. Okay, so again, the distance from the start vertex, we can see that in the table, from A to D is 2. We add 2, which is the distance from D to F, and we get a total distance from A to F, which is 4. Again, our algorithm says if the distance to the vertex F is less than the known current distance, which is in our table, then update the shortest distance in the table. Okay. Well, the current shortest distance to F is infinity. So the table is going to be updated with the new shorter distance. We've just calculated that the new shorter distance from A to F is 4. So let's update the current value of infinity with this new value 4 and update the previous vertex to D. Another shorter path. All right, we're getting there. We'll now add D to the list of visited vertices. So it moves from the unvisited list to the visited list. Okay, algorithm repeats itself again, which is what algorithms are supposed to do. Select the unvisited vertex with the smallest known distance from the start vertex A. Well, looking at our unvisited list, that would be, and the shortest distance, that would be C. And that becomes our new current vertex. Okay, well, that should say for C, not for D. I've got to make those changes in my slides. Okay, so for C, examine the distance to its unvisited neighbors. It only has one unvisited neighbor, and that would be E. All other neighbors have been visited. Okay, oh, I got a little animation problem there, but that's okay. Calculate the distance of each unvisited neighbor vertex from the start vertex. So we're going to calculate from A to E. So vertex E, so we have 3, which is the distance from the start vertex from A to C, which is shown in the table. And then plus 2, and I've already shown that there in my animation, which is the distance from C to E. That gives us a total of 5. Okay. If the distance to the vertex, in this case to the E, is less than the known or current distance, which is in our table, then update the shortest distance in the table. All right, let's take a look. The current shortest distance in our table, already updated the previous vertex there, sorry about that. The current shortest distance to E is currently infinity. So the table is updated with the shorter distance. Okay, so we've just calculated a new shorter distance from A to E of 5. So we're going to update the current value infinity with the new value of 5 and update the previous vertex to C, which I did earlier in my animation. A new shorter path. Can you guess what happens next? Okay, we're going to add C to the list of unvisited vertices, or visited vertices, excuse me. Remove it from the unvisited list to the visited list. Once again, we're getting there. We're getting there. Look, our unvisited list is getting shorter, and that's what we want. We want to get that all the way down. Select the unvisited vertex with the smallest known distance from the start vertex A. Okay. So looking at our unvisited vertices, that would be F. It has the smallest distance from A. For F, examine the distance to its unvisited neighbors, which only has one unvisited neighbor, E. All other neighbors have been visited. Okay. So we can see that the distance from A to F, which is in our table, is 4. We add the distance from F to E, our only unvisited vertex there, and that distance is 5. So we have a total of 9. So from A to E via F, and F is our current vertex, right? Would be a total distance of 9. Now, remember the algorithm says if the distance to the vertex E is less than the known current distance in our table, then update the shortest distance in the table. The newly calculated distance is 9. Total distance from the start vertex A all the way to E via F. However, looking at our table, we have a shorter path. It already has a distance of 5, which is less than 9, of course. And that is via C. So the table will not be updated. Okay. But we do add F to the list of visited vertices because now we're done with F. Okay, once again, and we're almost there, right? Select the unvisited vertex with the smallest known distance from the start vertex A. Well, that's easy. We only have one left, and that's E. Okay, for E, examine the distance to its unvisited neighbors. Well, there's nobody else in the unvisited list, so there's nothing to do. Okay, since there's nothing to do, we just add E to the list of visited vertices. So now we've got all of them from the unvisited list to the visited list, and our table is now complete. So now you've seen how Dijkstra's algorithm figures out the shortest path. Okay, so there it is again. All right. If you want to so hopefully that makes a little bit more sense to you now. Sorry about a couple of those little mistakes in my PowerPoint. I will update that, and at some point I'll update this video. Okay, so the end result is from our starting vertex A, we found the shortest path to each vertex from, again, that starting vertex of A. And there's a picture of Dijkstra right there. Looks like one of the original hipsters. All right, thank you very much. I hope this video helped. And hopefully I'll be making similar ones for some other algorithms. Take care. Thank you.